Alright, so let's describe the relationship between the two elements and explain your reasoning. So let's take a look at the atomic radius of chromium versus the atomic radius of W, which is tungsten. Now, in this case, we know that atomic radius decreases to the left of a period and up a group. And we know that, to the right of a period and up a group. To the right of a period and up a group. And we know that the atomic radius increases to the left of a period and down a group. Okay, so let's use this trend to explain the relationship between tungsten and chromium. Now you can see that chromium is above tungsten, directly above tungsten. So because tungsten is below chromium, we can use the increasing atomic radius trend, right? So this is the increasing trend in red, right? And the decreasing trend in blue. We can use the increasing atomic radius trend, and we can say that the atomic radius of tungsten should be greater than the atomic radius of chromium. Now, this isn't enough just to write this, right, or it's really straightforward. What you want to do is you want to do an explanation. Okay, so why is the atomic radius of tungsten greater than chromium? Well, we know that tungsten is found in the 6th energy level, chromium is found in the 4th energy level, so we can use the explanation that the shell number increases, and you can use variables to explain this. The shell number increases, which is proportional to an increase in core electron shells. Okay, so if we have more core electron shells, this causes an increase in the shielding effect. Okay, and recall that the effective nuclear charge is nuclear charge minus shielding. So shielding increases, the effective nuclear charge decreases. So because the shielding increases, the effective nuclear charge decreases, and when the effective nuclear charge decreases, then the force of attraction that governs the protons to electrons, the force of attraction will decrease, and because the force of attraction will decrease, the kinetic energy of those valence electrons, and electrons in general, will tend to increase, right? Because the valence electrons move further away from the nucleus, the size of the atom gets bigger and bigger. So that's why tungsten is bigger than chromium. Let's take a look at part B. We have we're comparing the atomic radius of tin versus zirconium. Right, zirconium is atomic number 40. Tin is atomic number 50. You can see that zirconium is located to the left of tin. So we know that the atomic radius increases to the left as well. So because of that, we can say that the atomic radius of zirconium should be greater than the atomic radius of tin, but we need to explain this a specific way. Well, if we go to the left of a period, we can understand that the nuclear charge decreases. If the nuclear charge decreases, this is proportional to decrease in the effective nuclear charge, or the force of attraction, or the force of the nuclear charge that an electron, a particular electron, will feel. Now, particularly, we'll be looking at valence electrons. As the effective nuclear charge decreases, then we can understand that the force of attraction will also decrease. If the force of attraction also decreases, right, there is a weaker force of attraction between the protons and electrons, then the kinetic energy of the electrons will increase. So if the kinetic energy of the electrons increase, namely the valence electrons, the electrons move further away from the nucleus and the size of the atom gets bigger. That's why zirconium is bigger than tin. Okay, so it's really important to understand, first of all, to memorize these trends, but also to understand how these trends come to be. Okay, let's compare the following atoms based on atomic radius as well as electronegativity. So we're looking at chlorine versus potassium. Chlorine here is atomic number 17. Potassium here is atomic number 19. Right, and we can understand the atomic radius will increase to the left of the group and down a group, right? So we can understand, based on this trend, the atomic radius of chlorine versus potassium, well, this is going to be a little difficult because of the fact that potassium is found all the way to the left and it's found one group down, right? So we want to kind of base this on just our explanation, right? So once again, this is a prediction, so it's as close to the possible the true atom, the atomic radius, right? So we're just trying to make a prediction based on our reasoning. Okay, so what you have here is if we can look at potassium, potassium does have a higher number of protons, but chlorine is going to have one less shell, right? So based on that notion, I'm gonna take higher precedence on the shielding effect, right? So I'm gonna say that the atomic radius of potassium is actually greater than the atomic radius of chlorine. Now, once again, this is a prediction. So as long as you create an explanation, there is no true right or wrong answer. There are a few exceptions here, right? But this notion of shielding does create a big impact on the size of an atom, right? So because I'm going to attribute this to shielding, now take a look at potassium here, and potassium is going to have a higher shell number, right? So the valence shell is 4 instead of 3, right? So because there's a higher shell number, now there's higher or a greater number of core electron shells. So because there's a greater number of core electron shells, then there's going to be a greater impact of the shielding effect. Now the shielding effect is going to cause a decrease in the effective nuclear charge. And because there's a decrease in the effective nuclear charge, then there is also a decrease in the force of attraction. So because there's a decrease in the force of attraction, the kinetic energy of the electrons is higher, so now they can move further apart. So because they can move further apart, the atomic radius should be greater, right? So I'm putting more emphasis on the shielding effect, and because of that reason, potassium, I'm going to say potassium is higher than chlorine is, right? Now let's attribute this notion also to electronegativity, right? And we stated earlier that as the atomic radius increases, the electronegativity will decrease, and vice versa. So it's an inversely proportional relationship, right? Now I'm going to say that the electronegativity of chlorine should be greater than the electronegativity of potassium, and the reason for this is because, once again, back to the shielding aspect, right? Although potassium has 2 extra protons, it has 1 extra shell, and because of that reason, the spacing of the atom is a lot larger, right? So chlorine is going to have less shell numbers. As a result, it has less core electron shells, and as a result, it has less shielding to accommodate for that. So there's the less shielding effect. Because there's less shielding, then what's going to happen here is there's going to be a greater effective nuclear charge, right? Because we said that earlier, the effective nuclear charge is the nuclear charge minus shielding. Well, if shielding decreases, then the effective nuclear charge is also, it's going to increase. The effective nuclear charge would increase. If this gets smaller, then this will get larger, right? So, and the shielding effect is a very significant effect, so that's why I'm going to give it priority. As the effective nuclear charge increases, then as the force of attraction will increase, and as a result, the electronegativity will tend to increase, right? And we can validate this by by posting up the electronegativity chart, right? So here's my Pauling scale. I'm just gonna show you guys this really quickly, right? And if we take a look at the Pauling scale, we look at the electronegativity here. The electronegativity of chlorine is 3.16, and the electronegativity of potassium is 0.82. So the biggest significant difference here is the fact that there is a shielding effect, right? Although potassium is larger than chlorine, it's significantly larger because shielding has a large impact, right? So that's why shielding has a very important relationship in terms of increasing the atomic radius and thereby decreasing the electronegativity, right? So it's good to understand how these things relate, but once again, these are all trends, right? So we are just making predictions based on this, right? But as long as we explain our predictions, that's going to suffice. Alright, let's compare the following atoms based on their periodic trends and explain your reasoning. So let's take a look at the atomic radius of gallium versus the atomic radius of manganese. And we're also going to be looking at the electronegativity of gallium versus the electronegativity of manganese. Hopefully at the end of this we can kind of attribute a relationship between atomic radius and electronegativity. Okay, so let's take a look at the atomic radius of gallium. Well, we know gallium is atomic number 31 and manganese is atomic number 25. And we can understand that atomic radius, if we recall, atomic radius will increase. I'm just going to look at the increasing trend for each of these. the atomic radius increases to the left of the period and down a group, right? So in this case, we can understand that the atomic radius of manganese should be greater than the atomic radius of gallium, right? And if I wanted to relate this, right, if I take a look at gallium here, 31, but take a look at gallium, you can notice here that the atomic number is greater, so the nuclear charge is higher for gallium, right? And if the nuclear charge is higher for gallium, then this tells us that the effective nuclear charge is also greater. And if the effective nuclear charge is also greater, then the force of attraction of the nucleus to the electrons is going to be higher. So if the force of attraction to the electrons are higher, then this actually reduces the kinetic energy of the electrons, right? Because now the electrons, there is a force that's holding the electrons back, it's limiting their kinetic energy, and it also causes them to basically move closer and closer in towards the nucleus. So the size of the atomic radius, right, which is the distance from the nucleus to the valence shell, is going to get smaller and smaller. So as a result, the kinetic energy decreases, the atomic radius of gallium decreases. So that's why manganese is going to be higher than gallium, right? Let's take a look at the electronegativity of gallium versus manganese, right? So if we're looking at electronegativity, electronegativity actually increases up a group and to the right of a period. So we can understand that the electronegativity of gallium should be greater than the electronegativity of manganese. Okay? So if the electronegativity of gallium is greater than electronegativity of manganese, if we're taking a look at gallium again, right, we can understand that because we're going to the right of the period, the atomic number increases, right? So the nuclear charge will increase, the number of protons increases. As a result, the effective nuclear charge increases, and because the effective nuclear charge increases, the force of attraction increases, and because the force of attraction increases, the electronegativity of gallium should be greater than the electronegativity of manganese. Now, let's cross-compare the atomic radius of gallium versus the electronegativity of gallium, right? So we stated that the atomic radius of gallium is less than, right? So we have this statement here that the atomic radius of gallium is less than the atomic radius of manganese, but then the electronegativity of gallium is greater than the electronegativity of manganese. This tells us that the smaller the species is, right, the closer the electrons are to the nucleus, the stronger the electronegativity, right? So the smaller the element is, the higher its electronegativity. And that makes sense because we understand that electronegativity will decrease due to separation distance, right? So if the separation distance decreases, electronegativity increases. If the separation distance increases, the electronegativity decreases, right? There is an inverse relationship. And likewise, right, we can understand that as the atomic radius increases, the electronegativity of a species will also tend to decrease. And if the atomic radius decreases, the electronegativity of a species will tend to increase. This is a general principle, right? Right, because we understand that as separation distance does increase, right, then the effective nuclear charge, right, the nuclear charge will remain the same, but the effective nuclear charge, which is dependent on distance, will tend to decrease. And if the effective nuclear charge tends to decrease, then the force of attraction tends to decrease, and essentially electronegativity is the force of attraction. So this is really our understanding of it. So it's good to understand how two different PRR trends will relate to each other, right? So we can explain all of this by looking at some of these key terms that we discussed. Ionization energies of aluminum versus magnesium, and then the ionization energies of carbon versus germanium. So we take a look at aluminum. Aluminum here is 13, and magnesium here is 12, right? So we can understand that according to what we talked about for our ionization energy trend, we know that ionization energy increases to, i.e. ionization energy increases to the right of a period and up a group, and ionization energy decreases to the left of a period and down a group, right? So because of this notion, we can thereby state that, I should use a different color for this actually, so ionization energy decreases to the left of a period and down a group. Because of this notion, I'm going to say that the ionization energy of aluminum is greater than the ionization energy of magnesium, right? So it's going to take more energy to remove the valence electrons in aluminum than magnesium, and we kind of stated this earlier where aluminum has 3 valence electrons, magnesium has 2 valence electrons, and we're going to have the total ionization energy for aluminum just off the bat here is going to be the first ionization energy plus the second ionization energy plus the third ionization energy. So just looking at the total ionization energy for aluminum, you have to add all 3 ionization energies together, right? So it's already larger than the total ionization energy for magnesium, which is the first ionization energy plus the second ionization energy, because magnesium only has 2 valence electrons. But if we were just going to look at our trend here, we can take a look at aluminum 13, and we can notice here that the atomic number is greater, right? And because the atomic number is greater, the nuclear charge is greater, and because the nuclear charge is greater, the effective nuclear charge is also greater, right? And because the effective nuclear charge is also greater, the force of attraction here is greater, and because the force of attraction is greater, the ionization energy is going to be greater. So you need more energy to take away the electrons from the nucleus, right? Now, one thing that we can understand here is if we compare magnesium to aluminum and we look at their electron configuration, right? And if I just look at their condensed electron configuration, if I was looking at magnesium, I can write this as neon, right? For 3s2. Okay, so it's 3s2. But aluminum here is basically neon 3s2 3p1. Okay, and you can understand that this is the p block here, right? So this is the p block, and then this here was the s block, right? So off this notion, the valence electron for aluminum here is further away from the nucleus than the magnesium atoms, right? So in that sense, there is a distance association, right? So like aluminum's electron configuration, you'll have the 3s, 2, but then you also have the 3p1 electron, right? So this electron it is a further distance. This is a further distance from the nucleus. So the ionization energy of this valence electron seems to be a lot lower than its s subshell counterpart, right? However, this distance here isn't going to accommodate for the fact that aluminum has 3 valence electrons, magnesium has 2. So because of this extra electron, then because of that aspect, the total ionization energy should still be larger for aluminum. Furthermore, aluminum also has a stronger nuclear charge, so that also kind of will attribute that. But it's also important to understand that there are differences of subshells, right? And although it doesn't make a significant difference like the shell number, which creates shielding, it is still important. There is still going to be shielding between subshells, and we're going to discuss this and how it relates to periodic trends very shortly. But for the time being, this will suffice in our prediction of the trends between aluminum and magnesium. Now let's take a look at ionization energy of carbon versus germanium. So I'm looking at ionization energy of carbon versus germanium. Carbon's here, germanium's down here, right? Germanium is basically 32, carbon here is 6, right? And you can imagine that germanium, the atomic radius of germanium should be a lot bigger. So I'm going to say, and we know that ionization energy decreases down a group, so I'm going to say that the ionization energy of carbon should be significantly greater than the ionization energy of germanium. If I take a look at germanium here, let's use a different color. But if I take a look at germanium, we can understand that the shell number increases, and if the shell number increases, what's going to happen here is there's more core electron shells, right? So if there's more core electron shells, then what's going to happen here is there's going to be an increased impact of the shielding effect. So there's more shielding now that exists, and because there's more shielding, the effective nuclear charge decreases, and because the effective nuclear charge decreases, the force of attraction will also tend to decrease, and when the force of attraction also tends to decrease, so does the ionization energy. There isn't a significant force that is holding the electrons in the atom, especially the valence electrons, which are the furthest away from the nucleus, and as a result it's a lot easier, it takes less energy to remove them. Okay. Specifically also, most elements in the same group tend to have the same valence electrons. However, transitional metals can have multiple valencies, right? So you also need to consider how many valence electrons you're considering, because there's going to be multiple ionization energies that you have to calculate, right? But for the most part, this trend will suffice. Okay, let's compare these elements based on their PR trends. So we're going to take a look at ionization energy, electronegativity, and atomic radius. Okay, so let's start with some of these trends. I'm just going to write down all of the increasing trends for each of these, just to recap. We know that ionization energy increases up a group to the right of a period, right? We know that electronegativity increases to the right of a period and up a group, and the atomic radius increases to the left of a period and down a group. Okay, so keeping this notion in the back of our minds, we're going to kind of compare these guys, right? I'm going to look at their increasing trend. So let's start with cobalt and vanadium. Now cobalt here is basically atomic number 27. Vanadium here is atomic number 23. And you can see that cobalt is basically to the right of vanadium. So because of that, we can understand that the ionization energy of cobalt should be greater than the ionization energy of vanadium. Okay, so it's going to take more energy to remove cobalt's valence electrons than vanadium. And the way we can explain this, I'm going to write this out here, right, for cobalt, right, the nuclear charge would be greater because now it has 4 more protons than vanadium, and as a result the nuclear charge, the effective nuclear charge would be greater, and because the effective nuclear charge is greater, then we can understand that the force of attraction that holds the electrons, specifically the valence electrons, is higher, and if the force of attraction is greater, then the ionization energy should be higher, okay, of cobalt, right? So that's explaining our initial statement. Let's take a look at the electronegativity of cobalt versus vanadium. We can say that the electronegativity also increases to the right of a period, and the electronegativity of cobalt is greater than the electronegativity of vanadium, and we can attribute this. If I look at cobalt here again, we can understand that the atomic number increases. As a result, the effective nuclear charge increases. As a result, the force of attraction increases, and we know that electronegativity is the attraction of the nucleus to the valence electrons. So this can explain that the electronegativity also increases. So we can see that there is a directly proportional relationship between ionization energy and electronegativity. It makes sense because if the electronegativity of an atom increases, that means that the nucleus is creating more of a significant pull on the valence electrons particularly, and as a result the ionization energy should increase, right? So, and vice versa, right? So that ionization energy and electronegativity, they should be directly proportional, right? So if the electronegativity decreases of an atom, then the ionization energy will tend to decrease. Okay, so this is really important to understand. Now let's also compare this to atomic radius. We know that atomic radius decreases to the right of a period, right, and it also decreases up a group, right? So, and we can understand that the atomic radius of vanadium, according to this notion, should be greater than the atomic radius of cobalt, right? Because vanadium is located to the left of the period, right? So we're still in the valence shell, in the 4th valence shell, and vanadium is located in to the left of that period. So we can understand that if I'm looking at cobalt here, When looking at cobalt here, we can understand that the nuclear charge is lower because there's less protons. As a result, the effective nuclear charge is lower, right? Because there is less effective nuclear charge, the force of attraction is lower, and because the force of attraction is lower, this tells us that the force that is attracting valence electrons specifically is weaker, and as a result, the electrons have more energy to move. The kinetic energy of the electrons is higher. The kinetic energy of the electrons is higher, they can move further out, and as a result, the atomic radius of cobalt is going to be, is basically going to be, wait, I think I'm in a mistake here. The atomic radius is higher. Sorry guys, this is vanadium, not cobalt, right? Because we said the atomic radius of vanadium is higher, so it's kind of lost in translation there. So this is for vanadium, right? So the nuclear charge is lower. As a result, the effective nuclear charge is lower. The force of attraction is weaker. The kinetic energy of its electrons, its valence electrons specifically, are higher. As a result, the atomic radius is higher, right? Now you can understand that the electronegativity is lower and the ionization energy is lower, but the atomic radius is higher. So this tells us that there is an inverse relationship, right? There's an inverse relationship between electronegativity and atomic radius, and there's an inverse relationship between ionization and atomic radius. So put this another way, if the atomic radius increases, then the electronegativity of the atom decreases, because now the electrons are further away from the nucleus, higher separation distance, and as a result, the ionization energy, because there's less of a pull holding the valence electrons, there's less energy needed to remove them, right? And vice versa, right? If the atomic radius decreases, then the electronegativity will increase, because now the electrons are closer to the atom, there's a stronger force of attraction, and the ionization energy will increase. So this is very important to understand the relationships between atomic radius, electronegativity, and ionization energy, as well as atomic radius and ionization energy. So sorry about that hiccup there, but try to understand this and try to relate the findings, try to relate these periodic trends. Okay, let's compare the following based on their trends. We're looking at electron affinity, so let's look at zinc and calcium. Zinc here is basically has an atomic number of 30. Calcium has an atomic number of 20. Right, zinc is way further to the right than calcium is. Right, so based on that notion, we know that electronegativity tends to increase to the right of a period and up a group. And electron affinity also, did I say electronegativity? I mean electron affinity also decreases to the left of a period and down a group. Okay, so now that we know this, based on this trend, we can understand that the electron affinity of zinc should be greater than the electron affinity of calcium. This tells us that more energy is released when we add an electron in for zinc than we do for calcium, and that as a result, it's easier to add electrons in for zinc than calcium. Now let's try to understand why that's the case, right? So in this case, if we're looking at zinc is 30, we can see that the nuclear charge is higher. The nuclear charge is higher, the effective nuclear charge is greater, and because the effective nuclear charge is greater, the force of attraction between the nucleus and the valence electrons is higher. The force of attraction is higher, then what we can understand here is that there's less resistance to entry, so there is a lower barrier energy. Because there's a lower barrier energy, if we look at our notion of electron affinity and barrier energy, I'm going to write that out here. Electron affinity is the energy released by adding in electrons into an atom, and we can take the kinetic energy of an electron as something that's constant. This is just the energy associated with any electron in free space that's untethered, subtracted by the barrier energy. So if this value here is constant, this is constant, then fluctuations in the barrier energy will affect the electron affinity. So if the barrier energy decreases, for instance, then this would be higher because now you're subtracting it. You're subtracting the kinetic energy, a constant number, by a smaller value, right? And so this is the idea. So as the barrier energy decreases, then what's going to happen here is that the electron affinity will increase. So it's an inversely proportional relationship, right? So in that sense, the electron affinity is inversely proportional to the barrier energy. Okay, so this is what we kind of went over last time, and that's the idea behind why the electron affinity of zinc is greater than calcium. Now let's take a look at the electron affinity of chromium versus molybdenum. So chromium has an atomic number of 24. Molybdenum has an atomic number of 42, right? And according to this trend here, we said electron affinity decreases going down the group. So as a result, the electron affinity of molybdenum should be less than the electron affinity of chromium. Okay, so why is that the case? Right? Why is the electron affinity decreasing down the group? Well, in this case, if we're looking at molybdenum for a second, right, the shell number is increasing, right? Because now you can see that the valence shell is the 5th shell versus the 4th shell for chromium. Shell number increases, so the number of core electron shells will tend to increase. If the number of core electron shells increases, the shielding effect tends to increase. When the shielding effect increases, what's going to happen here is the effective nuclear charge decreases. So because the effective nuclear charge decreases, the force of attraction decreases between the valence electrons and the nucleus, and as a result there's more barrier to entry. Shielding, furthermore, will also cause repulsion forces, which increase the barrier energy, right? So this is another thing that you want to kind of think about, right? We know that force of attraction is inversely proportional to barrier energy, but shielding, on the other hand, as shielding is directly proportional to barrier energy. As shielding increases, the barrier energy increases. There's more resistance, right? Because shielding causes repulsion forces, which resist electron addition. Same notion with barrier energy. Right? And as barrier energy goes up, the electron affinity goes down. Okay, so it's really important to understand, right, the notion of electron affinity, barrier energy, and how this kind of will tie in together. Okay. So based on this notion, we can kind of see that more of the nonmetals, right, to the right of the period, the nonmetals tend to have large electron affinity, so that means it's easier for them to add electrons into their network, their electronic network, and metals tend to have low electron affinity. So that's one of the reasons why they don't tend to gain electrons as spontaneously as nonmetals, and they prefer to lose electrons. So all of these things will tie in, and we'll kind of relate these periodic trends later when we look at reactivity. Okay, so let's compare the following atoms based on their periodic trends and explain our reasoning. Okay, so in this case we have the atomic radius of phosphorus, atomic radius of arsenic. So we're comparing phosphorus and arsenic. We're going to look at 4 different trends: atomic radius, ionization energy, electronegativity, and electron affinity. So let's take a look and let's cross-compare some of these trends, and let's see what kind of general consensus we can get from this. Okay, so let's start with the atomic radius. So I'm just going to write down all the increasing trends up here. I'll do that in red. The atomic radius increases down a group and to the left of a period. The next trend, ionization energy, increases to the right of a period and up a group. The next trend, electronegativity, increases to the right of a period and up a group. And the last trend, electron affinity, increases to the right of a period and up a group. And you can think about the opposite trends in the opposite directions, right? So this is a great way to memorize this. Okay, so let's start with the atomic radius. So according to this trend of atomic radius, we can notice that phosphorus is 15, arsenic is 33. Arsenic is right below phosphorus in group 15. So in this case, we can say that the atomic radius of arsenic is greater than the atomic radius of phosphorus. And if I looked at arsenic here, right? We can imagine that the shell number of arsenic is greater than phosphorus. If the shell number is greater, that there is more core electron shells that are present. If there's more core electron shells, then we have a higher impact of the shielding effect, which will cause electrons to be pushed further away from the nucleus. And as a result, if the shielding effect increases, the effective nuclear charge decreases, right? So the effective nuclear charge diminishes due to more shielding, and as a result, if the effective nuclear charge decreases, there is a weaker force of attraction that governs the electrons, and this means that there is more kinetic energy of the electrons, so the electrons can actually move further and further away, causing the atomic radius to increase. Okay, so that's our relationship of atomic radius. Let's take a look at ionization energy, do some different color. And we know that ionization energy trend increases to up a group and to the right of a period. Well, because we're going down a group to arsenic, if we're looking at arsenic, the ionization energy of phosphorus should be greater than the ionization energy of arsenic, right? If we kept looking at arsenic, and I'm just going to look at everything in terms of arsenic so we can just kind of cross compare all of these periodic trends at the end, right? As if we're looking at arsenic, the shell number goes up, right? As a result, there's more core electron shells, so therefore the shielding effect increases. Because shielding increases, the effective nuclear charge decreases, and because the effective nuclear charge decreases, the force of attraction that governs the valence electrons will tend to decrease. So if the force of electrons that govern the valence electrons is lower, then it's a lot easier to remove the valence electrons in arsenic. Okay, now you can understand that this is going to be dependent on how many electrons you want to remove for arsenic, right? Because arsenic is a transitional metal, you can have multiple valencies. However, for the most part, it will take less energy per each electron, right? So we're just going to look at it in general. Obviously, there's multiple factors involved, right? But we're just looking at a general view of it. So that's why the ionization energy of phosphorus is greater than arsenic. Let's take a look at electronegativity of phosphorus versus electronegativity of arsenic. Once again, electronegativity also increases to the right and up a group. So as a result, the electronegativity, because arsenic is one group below phosphorus, the electronegativity of phosphorus should be greater than the electronegativity of arsenic. So we looked at arsenic here, 33. As the shell number increases, the shielding effect increases. So it's the same idea here. I'm just kind of reiterating it all, right? It's good to kind of look at this. Shell number increases, the shielding effect increases, the effective nuclear charge will tend to decrease. The effective nuclear charge decreases, the force of attraction decreases, and really electronegativity is a force of attraction by the nucleus to the valence electrons, so electronegativity will tend to decrease. Okay, so that happens there. And the last case here, we have electron affinity. Okay, so let's do that in blue. The electron affinity here also increases to the right of the period and up a group. Well, in this case, because we're going down a group, the electron affinity of phosphorus is going to be greater than the electron affinity of arsenic. So if we're looking at arsenic again, okay, as the shell number increases, what's going to happen is there's an improved shielding effect because there's more core electron shells like we've mentioned earlier. Because there is increased shielding effect, there is basically a decreased effective nuclear charge, which means a decreased force of attraction. And because there's a decreased force of attraction, there's more resistance to entry, right? So the barrier energy is actually higher, right? So the barrier energy is higher, and we understand that the electron affinity is equal to the kinetic energy of an electron, which is constant, subtracted by the barrier energy. So if the barrier energy is higher, the electron affinity is lower because, oops, let me just fix that up, because of the fact that this guy here is constant, it's fixed. So as a result, the electron affinity is lower. Now if we cross compare all of these things, we can understand that ionization energy is related to electronegativity, atomic radius is inversely proportional to ionization energy and electronegativity. And ionization energy, electronegativity, and electron affinity are related because, once again, these both will consider the attraction of the nucleus to the electrons, which will basically limit or lower the barrier energy, which creates the electron affinity, right? So collectively, what we can say here is, I'm just going to summarize all of this, but ionization energy is directly proportional to electronegativity, which is directly proportional to electron affinity, right? And atomic radius is inversely proportional to each of these, right? The atomic radius is inversely proportional to electronegativity and inversely proportional to the electron affinity, because the further the atomic radius, the larger the atom becomes, the weaker the force of attraction governing the valence electrons, right? And you guys can kind of try to understand this. So collectively, this, you can write this as 1 over AR, right? So that's the relationship between all of these trends, right? And it's good to kind of understand that and how they influence each other.